we put atomic structure and periodicity, or the periodic table, together because of the way the periodic table is structured. If you know how the periodic table is built, how it's laid out, then it will tell you how to position your electrons. If you're trying to write out the electronic structure for an atom, which we'll learn to do in a second, then the periodic table will guide you to do that. You can do it without the periodic table if you use a set of rules, but it's a whole lot easier if you know how the table's set up and use it. So the information that we get about atoms, actually about the whole universe, up until the 20th century when we started sending actual probes out into the solar system. Now we've got a couple that are past the solar system. Voyager 1 and 2 have left the solar system officially. But the rest of them have stayed in the solar system and they've sent us back information. A couple of them have actually gone to comets. One went to the moon and returned, well, actually the Apollos returned samples from the moon. But we've had some that went out and sampled comets and brought the samples back. Outside of that type of information from the universe, everything else we get from the universe is from light. Whatever matter is doing out there and sending us information using light. And this is just an example of the information, type of information we can get from elements is the way they're used in fireworks. Certain types of elements, when they're excited with the explosive charge, they give off different colors. Some are easier to make than others. So if we want to find out some things about, learn things about elements, we want to know why those different colors are developed, because they seem to be unique for each element. I say that with tongue in cheek because our eyes are not discriminating enough to tell the difference between, say, calcium and sodium. Now that's a good picture. So calcium and sodium, we can see the difference. But if you're doing a flame test in the laboratory, you may not be able to tell. It depends on the solution that they're in when you put them in your loop and then stick them in the flame, or how hot the flame is will give you a different color. So we need something a little more precise, a little more accurate, more discriminating than our eyeballs. Now, some people can tell the difference between, say, I don't know, you ever seen the movie Steel Magnolias? Yeah, where Julia Roberts is planning her wedding and she wants a certain, the pinks. Yeah, this is blush and that's bashful. I can't tell the difference. But maybe if we had a spectrometer, we could discern the wavelength differences. And that's what we use to actually get more discriminating with the elements. So we want to know, why do they give us these colors? That's information that we can use to identify the elements. In fact, I used to use an instrument called an inductively coupled argon plasma spectrometer, which is a mouthful. But it excites the elements in a sample, most of them metals in the work I was doing. And then it spreads that light out and picks out individual wavelengths, maximum wavelengths that are being emitted by the sample. Can use those to do two things: identify the element, be sure I've got the right element, and then the intensity of the wavelength will tell me how much of it I have. Now, these colors, if they're in a flame test, we get certain colors. if they're in a solution, they might give us a different color. Let's see. I don't see copper in there. But if you have, say, copper sulfate in solution, in aqueous solution, it's going to be blue. If you stick it in a flame, it may come out green. So there are differences in there, the way that light is produced. And we want to know why some colors are characteristic of different chemicals. Some of the colors are actually unique for the element. Actually, all wavelengths that we get from spectrometer are unique for the elements. But we can also get different colors from the same group of elements. They're just in different arrangements in the molecule. And those arrangements in the molecule will give you different colors, different wavelengths. Here's an example. Hemoglobin. When hemoglobin, anybody had anatomy and physiology? Okay. So you know hemoglobin is a very complex molecule. In fact, it's 4 proteins together, and each protein has a heme ring structure in it. And inside that ring structure is an iron atom. So you have 4 iron atoms per hemoglobin molecule. And each one of those oxygens can associate or attach to an oxygen. And that's how oxygen is carried throughout the body. When the oxygen is attached to that iron, it changes the structure of the molecule so that it's a bright red color. So if you get, say if you're having blood gases done, they have to go down and hit an artery, not just a vein, to take blood samples. They usually go in through the wrist. It's easier to get to it. And it takes a really skilled phlebotomist to hit it right, to find that artery, and then hit that artery to get your blood gases. Well, the blood that comes out is going to be bright red. If you get blood from a vein, it's going to look kind of like, it's going to be a bluish color, a bluish red, sort of. As long as you keep it away from oxygen, away from the air. As soon as the air hits it, it goes red because it's picking up oxygen. And that slight difference between the presence of oxygen and absence of oxygen changes its color. My master's thesis was on, I was in food science at that time, was on crawfish processing waste. Down in Louisiana, during the crawfishing season, there were some companies that would take fresh crawfish in from the farmers and cook them and peel them and take the meat and freeze it and send it all over the world. Well, only 15% of a crawfish is meat in the tail. The rest of it is waste. And these companies were staring at EPA intervention because of their waste. Now, the shrimping industry was undergoing the same problem, only more of the shrimp is meat than the crawfish is. So the crawfish industry had a bigger problem per batch, maybe not as a whole because it's a smaller industry. Anyway, that red color that's in their shells, and you can see that same color in lobster shells, that red color, is due to a class of compounds called carotenoids pigments. And the particular one that I was interested in for my processing was called astaxanthin. And that's what the molecule looks like. Notice it's got all those double bonds in there. When you see a double single, double single, double single, those bonds are, and the word just flew right out of my head, conjugated. Conjugated double bonds like that, the more of them you have, the lower the frequency, and you move from one end of the spectrum to the other, moving toward the red in this case, because we have so many of them. The vitamin A molecule is about half that size. It's only got half of it. So it's not red, it actually moves up into the orange. That's why your vitamin A in carrots and some citruses will give you the orange color instead of the red. So if we're going to get information from light, we need to know something about light. And this is more physics than it is chemistry, but we need to know about it. So we can characterize light, and light has been studied this way for quite a while. One measurement we can make of light is its wavelength. And we use the small letter lambda, Greek letter lambda, for wavelength. And the measurement of wavelength, the units of measuring in wavelength is meters. That's the standard SI unit for meters. Now we use other units, but this is the SI unit. What does the wavelength mean? Let's see, I think I have slides on this, so I may be able to save myself some headaches. I'll just put them up on the board first. Wavelength is meters. Frequency, which is the Greek letter mu. Some textbooks now are just using F instead of that to avoid confusion. But traditionally, lambda, mu, frequency is how many wavelengths pass a point in space in a second. Right. So if you have, say, a signal on your radio that's 101 kilohertz, that's 1,000 wavelengths per, no. Yeah, 1,000. That's 100,000. 101 kilohertz is 100,000 or 101,000 wavelengths passing a given point in a second. Okay, so the units are hertz, but hertz, it's in honor of a researcher from olden days. But the units of measure would be like cycles or wavelengths per second. And since cycles is not a unit of measure, it's usually given as reciprocal seconds. Right? Meters, reciprocal seconds, because seconds is in the denominator. And then the last one we have is the speed of light, which is given as c. And in a vacuum, it's pretty close to what it is in air, so we generally use this vacuum, and it's a constant. And it's 2.9979 times 10 to the 8th meters per second. So it covers a lot of ground really quick. Okay, how they're all related. This constant is equal to the wavelength times the frequency. I better do that better. That's starting to look like a gamma. There we go. So if we check our units, right, this is in meters. This is in reciprocal seconds, right? Meters per second, meters per second. We're good. All right, so what does a wavelength look like? Well, remember, these things are happening in 3 dimensions. So when I put it on the board, this is a representation in 2 dimensions of a wave. And actually, we can speak of waves for light, for sound, for a number of other things. Geologists use them all the time to measure position and strength of earthquakes. But for our purposes, we're going to talk about light. So the representation, if the light is moving in this direction, then it's going to have an amplitude like this, maximum, and then it's going to go down through the direction we're going, and then negative, and then positive, and then negative, and positive, and just keep going. So a wavelength is the distance between, the easiest way to do it is between two crests. So between here and here is a wavelength. It could be from any place. It could be from here to here. But if you do it anywhere else but the crest, then you got to be sure that your measurement is on a position on the wave that's headed in the same direction. Like just because it's on this side there, you can't use this side. It has to be over here. So crest works the best. Or you can use troughs. Crest versus troughs. Now, what about frequency? Well, if we say position our eyeball here, and we watch the crest as they pass, then the next one passes. How many of those can we see in 1 second? Okay. What you'll notice from the formula, let me separate it here. Speed of light equals lambda times frequency, is that if this is a constant, and remember our gas laws, like Boyle's law, pressure times volume equals a constant. Okay. Whenever you have two variables as product equal to a constant, those variables are inversely proportional to each other. So as this one goes up, that one goes down, or as this one goes down, that one goes up. So as the wavelength gets shorter, the frequency gets faster. You see a higher value for frequency, and that makes sense. I mean, if you squeeze this down and make a shorter wavelength, then over the same period of time, you see more waves passing your eye in a second. And that's what that slide is trying to show. The frequency of the first one would be 4 hertz, or 4 cycles per second. If we cut the wavelength in half, then we're going to see 8 cycles per second. And if we cut it in half again, we're going to see 16. So as you make the wavelength smaller, the frequency gets bigger. And waves on a pond are similar. Sound waves work that way too, only they operate at a slower speed and different wavelengths. Okay. Now that we know how to characterize light, when we actually look for it, we see that we can get a wide range of frequencies and wavelengths. And this slide is trying to show that if we go from left to right, and as we go to the right, we're actually increasing the wavelength. Increasing in that direction. Increasing to the right. And somewhere in the middle here is a very small sliver of the visible wavelengths, stuff that we can see. You know, some animals can see outside that range a little bit on either side. But inside here, the visible spectrum, all our colors, the longer wavelength of visible is red. And the shortest one is violet. Right? Did everybody memorize that mnemonic from grade school? colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. Yeah. Although it should be flipped for the way we've represented here. Now the reds are going to be the longer wavelength right there on this side. Violet, the blue end, be the shorter wavelength. And then between the reds and the longest wavelengths are going to be radio waves. And that's exactly what radio waves are, where we find AM radio, FM radio, shortwave enthusiasts communicating with other shortwave operators all around the world. And they can do that for because of the Earth's ionosphere. Particular wavelengths, you send them off in all directions, but some of them go up and bounce off the ionosphere and go around the curve of the Earth. And sometimes they can bounce up, down, up and down. You can talk to somebody on the other side of the planet. It may not be very clear, but you can still communicate. And then the next shortest wavelengths are microwaves. Right? We use those for communication and cooking food. And then down here is infrared. Right? Infrared means, infra means underneath. And then on the other side, we have ultraviolet. Okay, those are the ones that give you sunburns. And then X-rays, right? That's how you get your CAT scans. And then the shortest wavelengths are gamma rays. Okay, so if the wavelength is increasing this way, the frequency is increasing this way. Right? And we're going to learn in the next slide or two that as the frequency increases, so does energy. Right? The highest frequencies give us the most energy, or the shortest wavelengths give us the most energy. Have you heard in the news about gamma ray bursts coming from space? Yeah. The gamma ray burst, they're not real sure what causes them, but they do know that they're directional and they're extremely powerful. They could be coming from black holes. They could be coming from newly created black holes. They could be from other types of exotic astronomical events. But they're extremely powerful energy forms of light. And since they're directional, we're probably not at a great risk, because these gamma ray bursts, they can be coming from billions, and billions of light years away and still have enough power to strip the atmosphere off the Earth if we get a direct hit. Right, so we're talking about a lot of energy. Gamma rays can also be produced in small amounts from nuclear events, like an atom bomb will do that, or in a particle accelerator. You get things going really fast, like close to the speed of light, one going this way and one going that way, and they smash, and they can give off some gamma rays. So very energetic events. When we talk about energy, there's a law in thermodynamics that's called, and we'll get into this in more detail in the second semester, but it's called the first law. First law of thermodynamics. It simply says that the amount of energy in the universe, I should put universe here, is constant, doesn't change. So what that means is we can convert energies from one form to another, but we can't create energy, we can't destroy energy. You've got to account for it. It's like a budget. So if we have electrical energy, in this case, it's probably a direct current, and you send it through these forks that are stuck in the pickle. If you get enough current going through that pickle, you can heat it up, and it gets so hot that it gives off light. All the energy that's going into that pickle must be accounted for. Some of it is converted to heat. Some of it goes through the pickle and out the other side. You don't have to account for that. And some of it is converted into light. Okay, now a little history lesson here. James Clerk Maxwell was a brilliant mathematician and physicist. And in the middle of the 19th century, about the time we started our Civil War, he published a series of equations that described electromagnetic radiation, which by that time they understood it to be, or light, in terms of its wave nature. And we call it electromagnetic radiation because it has these two components embedded in the light beam. It has an electrical component and a magnetic component. We're not going to go into that detail right now, just so you know. And these equations are still valid today under circumstances that address the wave nature of light. The reason I say the wave nature is because light it's like a split personality. It has wave nature and particle nature. To a certain extent, maybe not completely, but to a certain extent, these equations still agree with modern theories, physical theories of general relativity or quantum mechanics. General relativity speaks to events in the universe of huge mass and high speeds, like very close to the speed of light, and masses on the order of neutron stars and black holes. That's where Newtonian physics just falls apart. Or if you get really, really, really small, like electrons in an atom, then you need to go to quantum mechanics. And let's see, yeah, we get a taste of that, I believe. Yeah, toward the end of the course. Taste of quantum mechanics. Actually, we're going to get some of that today. Yeah, we're going to get some of that today. Okay, scientists made a huge mistake. Not all of them, but a lot of them did. At the end of the 20th century, they thought, whoa, we got all these equations that work, right? Our job is essentially done. All we have to do now is just refine, work at the edges and refine them a little more. What they didn't realize was they had just scratched the surface of what actually goes on in nature. So along comes Max Planck at the turn of the 20th century, beginning of the 20th century. He was studying, among other things, Max Planck was studying, and he's a German. He was studying a black body radiation. What we mean by black body radiation is like that pickle, except it's even more than that. The pickle, if you shine light on it, it'll give you a green reflection. Black bodies, if you shine light on them, you get nothing back. They just absorb energy, and they only give off light when they get hot enough. So there's a relationship between the temperature of a black body and the color of light it emits. So that's how we get information about stars. Some stars are blue colored. Some of them are, like our sun, are kind of yellowish colored. And there's some that are even red colored. Have you ever, you know where the constellation Orion is located? No? It's Orion the Hunter. It has 2 stars up here, it has 3 in the belt, and it has 2 for his knees. And one of those stars, I'm trying to remember which, is one of his shoulders, I think, is the star Betelgeuse. It's like the movie. But it's a red giant. And with a pair of binoculars, you can get a good look at it. And it's definitely red. But you can look at other stars and they're blue or white. That's due to their color. Their temperature. The temperature on their surface, according to Max Planck, is correlated with their color, their emission spectrum. So that's how we get information about the temperature, the surface temperature of different stars is by their colors. Well, Max Planck also came up with an equation that talked to this relationship right here. All right, so he said, he published this equation. The energy of light is equal to some proportionality constant, Planck's constant, times the frequency. So if you know the frequency in reciprocal seconds, and the units of measure for this one are joule seconds, seconds cancel, leave you with joules. So this is, I think it's 6.626 times 10 to the minus 34 joule seconds, I think. Maybe I may have this last digit off, but I'll correct it when we get there. And what he also discovered was that this energy is delivered in packets. We call that quantized. In other words, it only comes in discrete units, discrete samples of energy. And that sample is based upon the frequency. So this was one of the first indications that light is not always a wave. I mean, we're relating its particle nature to its wave properties, but still, there's an indication here that light functions in a quantized relationship as particles, individual particles. You don't have anything in between. You just have, you either have this one, or you have this one, or you have these, or you have these, but you don't have anything in between. That's what we mean. So there's the, oh, I remembered something. There's Planck's constant, and it's simply a proportionality constant. Sometimes we call them fudge factors, to equate this value, this variable with that variable. Now, if you know the frequency, you can plug it in there. If you don't know the frequency, then we have to go to this relationship and just solve for the frequency and plug it in here. So now it becomes this, like that. Oh, those particles we call photons. Okay. And Star Trek made good use of that early on in the, let's see, it was late 60s, I think. Photon torpedoes. Oh, we gotta, let's see if this video is gonna play.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also— What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
There. Okay, so before I get into that discussion, you didn't already know, physics is a strange animal for as far as a science goes. It's split into two job descriptions. One is theoretical physicists. All they do is think and write math equations to try to explain things, and that's what Einstein was doing. Millikan was the other type of physicist. He was also a chemist, but in this case, he was working physics, and he was an experimental physicist. And a branch of physics, astronomy, they do similar type arrangements. So when Einstein proposed that light was had both particle and wave nature, and Millikan, we saw Millikan in earlier chapters. He was the one who gave us the mass of an electron. Remember that with the oil drop experiment? So they both got Nobel Prizes, one for the theoretical part and one for the Millikan for the experimental part. And strangely enough, well, maybe not strangely, but Einstein at the time he came up with this theory was working at the patent office in Switzerland for the government. He would spend a few hours in the morning, go to work, and review patents, patent applications to see if they were worthy of granting that particular protection from the government. And that would take him maybe a couple of hours. The rest of the day, he'd just sit at his desk and think and work things out on paper. So he did several groundbreaking things while he was at the patent office. So what does the photoelectric effect have to do with quantum nature of light? Well, these are the observations Up until this point, when the wave nature was the only way that they understood light, they thought that all you needed to do was increase the intensity of the light. And the light would cause the electrons to sympathetically vibrate as the light struck them. And the understanding there was that all you needed to do now was increase its intensity, which would add more energy, theoretically. And at a certain intensity, an electron would be ejected. But they found out that it didn't matter how intense you made red light, it would never eject an electron. So we had to go back and start over. That's what Einstein did. And using Planck's work and some others, he was able to show that it wasn't the wave nature of light that was doing it. It was the particle nature. These wave packets were the delivery mechanism for energy for the electrons. And as your light gets bluer and bluer and bluer, even into the ultraviolet, they carry more energy per packet based upon Planck's equation. And at a certain frequency, the threshold frequency, you had enough energy for, and it varies for each substance, usually metals. After you get down to high enough in your frequency, or blue or ultraviolet, then you have enough energy to eject an electron. Okay, you reach that minimum threshold energy. You can, so if you have your metal surface here and your light coming in and it's of a particular energy, then you can take an electron to what we call infinity. In other words, it's free from the atom. So you have this electron that's just barely free from the atom. That's what the threshold frequency does. Now, if you have more energy in your packet than is needed for that electron, then that electron will be given some momentum, will be given some extra energy. It'll be given kinetic energy, which means velocity. So what's left over from the threshold frequency gives that electron some oomph. Below that frequency, you don't get any electrons, no matter how intense the light. Intensity in this understanding is just you have more packets coming in. And none of those packets have enough energy until they reach the threshold. None of them have enough energy to eject an electron. So what happens to all that energy? Well, if it doesn't reflect, right, if it doesn't just bounce off like a mirror, then it may be absorbed by the metal. And in that case, those packets are called thermal. They're let's see. Must be on the next slide. Thermal radiation. There it is, thermal photons. Let's see, did I skip something important? I better go back. Once you reach the threshold energy and anything above it, then you can eject an electron. But the only thing that intensity does when you throw more photons at it is just give you more electrons. And those electrons that are ejected will still have the same kinetic energy. And it can be measured. Okay. Those are conclusions. We're just kind of rehashing there. I did mention the thermal photons. If they don't eject an electron, the energy has to go somewhere. And excess energy is converted into kinetic energy. Okay. Okay. So what does photoelectric effect tell us about the structure of the atom? That's what we're actually aiming at, what we're trying to get at. Because light can tell us some things about atoms. The interaction that we see between light and atoms happens with the electrons. You don't shine light on this metal and see nuclei jumping off. It's only the electrons. And the electrons are based upon what we learned in previous chapters. The nuclear atom has a nucleus here with protons in it, maybe some neutrons, and then electrons out here. Right? Electrons out here. Well, when light comes in, the first electrons to leave that atom are the outermost ones. So the energy relative to the nucleus, the energy is higher out here and lower down here, which just means that it takes more energy to eject this one than it does that one. So the photoelectric effect will eject that outermost electron. All right, the photoelectric effect, you know, I kind of take issue with that number 2. The reason being, well, actually, okay, let me see if I can explain this. The amount of energy required to go from here to infinity, that is free from the atom, is that threshold frequency. That's all that's needed to get it loose. So that's a quantized amount of energy, this 0. Anything greater than that, we transfer it to the electron as kinetic energy. So it's not, we're not saying that anything above the threshold energy will eject a different electron. It'll just eject that one and make it go faster. So in that respect, it is quantized. A certain amount of energy is required. The threshold frequency will get that electron loose. Okay, I already said that. I almost missed this one. So if this electron has kinetic energy, that means it has mass. And by this time, we were pretty sure that electrons had mass anyway, due to the work of J.J. Thomson, followed by Millikan. All right. That's my favorite picture of Albert Einstein in his golden years, showing off to the camera. There are other pictures of he was riding his bicycle, sitting on the handlebars, facing backwards. I like this one better. Okay, so he also, in the same year, he came up with the theory of special relativity. And in it, he proved mathematically that light has mass. And he came up with the equation that everybody seems to know, E equals mc squared. Now, this is the rest mass. There's something called relativistic mass that all matter possesses as it gets closer to the speed of light. So another part of his theory said that the closer you get to the speed of light, the higher your relativistic mass goes. And it goes to infinity at the speed of light. So that's why our conventional rocketry will never get us to that speed, because it would take infinite energy to overcome infinite mass. So we have to work out something else. You know, Star Trek's already done it with the warp drive. You just warp space and trick space into thinking that you're standing still when you're actually, it's like surfing a wave. That's another discussion. All right. There you go. So Einstein proposed this special theory of relativity, and there are various parts of it, but we're focusing on this particular relationship between light and mass. Energy and mass. Then Arthur Compton, who was an experimental physicist in 1922, actually confirmed that that relationship between light and mass. Okay, so electromagnetic radiation has a dual personality. You know, sometimes it behaves as a wave, sometimes it's pure particle, and sometimes it's both. Okay, so we make use of particle nature sometimes. Sometimes we make use of wave nature. If we're looking at the wave nature of light, one of the things that light does, based upon its wave nature, is diffraction. Diffraction is simply well, let's put it this way. Say you have a slit and you got this wave moving in, this light wave. When it reaches that slit, if light were a particle under these circumstances, and we had a detector over here, then it would come straight through, make a bright spot right there, and the rest of it would be unexposed, black. But it doesn't do that. It makes this bright spot, but it gets dimmer and dimmer as you go out, like this. And so it kind of spreads. So what that tells us is this light has used this slit as a origin point source for a new wave. And it exposes our detector with less intensity down here, simply because of the inverse square law. You know, the farther you are away from the energy source, the dimmer it is. And if you're twice as far away, if you're from here, you go twice as far, it's going to be a fourth as bright. Okay. If you go 3 times as far, it's going to be a ninth as bright. It's the inverse square. That's diffraction. You can also see it at the edge, corners of, say, a barrier, and lights come along here, and this edge serves as a point source. So if you're out in strong sunlight and you're looking at your shadow, or you hold something up with very sharp edge on it and look at its shadow on the ground, you won't see a sharp edged shadow. It'll get kind of fuzzy at the edge. And that's because of this diffraction. Another phenomenon of waves is refraction. There's a difference between diffraction and refraction. Refraction is the bending of light as it passes from one medium to another. So my glasses do that for me. They refract light. So if light comes in like this in its wave and it reaches this barrier, right, then it slows down. If this is air and this is glass, we know that light travels slower in glass than it does in air. So when it reaches this glass, right, this wave, it's going to slow it down. Slow it down. And that actually changes its direction. That's not a very good example. Very well drawn, but there's a difference in this direction and that direction. And if you grind your lens properly, you can have light coming in, and on this side it bends it this way, and this side it bends it that way. and changes the focus. That's refraction. And then the particle nature of light is shown very convincingly by the photoelectric effect. All right, so now let's try to take what we've learned about light and relate it to an atom. And we're going to start with the very simplest atom that we can find, hydrogen. If we, excuse me, if you use, I don't know if you did as a kid, if you use a magnifying glass and you go out and burn ants, right? Well, that's not all you can do with a magnifying glass. You can use the magnifying glass, or actually a prism would work better, right? One of those angular pieces of glass. And on the ground, you see the continuous color spectrum of light coming from the sun. And it's not actually continuous, but for argument's sake, let's say it is. It shows every color in the rainbow. Right? That's continuous spectrum. If we take an individual element like hydrogen and excite it to temperatures of the sun and let it, when you add energy to it, then it's going to re-emit that energy, right? We can't create or destroy it, so it's going to re-emit that energy as light. When we do that with hydrogen, or for any element, it will emit light in discrete wavelengths. For hydrogen, there are 4 of them in the visible range. There are others in the ultraviolet and the infrared, and they're useful for other purposes. But for our argument's sake, let's say in the visible range, we have these 4 wavelengths of light that are emitted by hydrogen when it's excited. And that's what it looks like. It's not animated and narrated anymore because this is because the format is not supported any longer. I forget which one was that they got rid of. I can't remember the name of it now. It's been too long. Anyway, but I wanted to keep the picture, and that shows you a continuous spectrum. All right.
The discharge tube is filled with hydrogen gas. When a high voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra due to the appearance of bright lines.
I guess that's it. Oh no.
In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay, so we're using things that we haven't talked about yet in there, the N, the 1, 2, 3, 4, 5, 6. We're going to get to that in just a second. But what we're trying to show here is that the electron outside the single proton in the nucleus can only occupy certain levels. So when it jumps from one level to the next, from the, say, 6 down to 2, that gives you, the bigger the jump, the more energetic the wavelength, or the shorter the wavelength. So that jump from 6 to 2 gives you 411 nanometers. The 5 to 2 gives you 434. The 3 to 2 gives you 486. And the, no, 3 to 2 gives you the red, 656. The 4 to 2 gives you 486. So what we're saying is that the movement of electrons around the atom, they occupy energy levels in discrete units and nothing in between. Now there's a, I don't know if it's a good explanation, but it's a rationalization for that. And we'll hope we may get to it. I'm not sure yet. So what the line spectrum tells us is that only certain energies are allowed for the electron in the hydrogen atom. And this, over time, we've learned that this is true for all atoms. The electrons can only occupy certain discrete energy levels outside the nucleus. I think we've already answered that question. Spectrum is not white for hydrogen because it only has those wavelengths. And the position and the movement of electrons is quantized. If they were not quantized, if the electron could move anywhere it wanted to, then hydrogen would produce a continuous spectrum. Right? All the elements would do that, and then we'd have no way to distinguish one from the other. All right. So with this understanding, Niels Bohr, who was a Danish scientist, proposed this planetary model. Let's see, Bohr's planetary model. It had its flaws, but it was a starting point. So he modeled the atom on the solar system. The sun would be the nucleus, okay? There's the nucleus. It has its protons in it, and some of them have electrons. But Bohr discovered that his theory only worked for hydrogens or other elements, excuse me, that only had one electron. So for hydrogen, that would be neutral. For helium, he'd have to remove one of the electrons and make it a +1 charge. For lithium, he'd have to remove 2 electrons and make it a +1, +2 charge. So as long as you only have one electron out here, his theory will work and his mathematics works. But he said there are discrete energy levels out here, right? And he gave them numbers. The first one is 1. The second one is way out here. The third one is a little bit closer. And they get closer and closer still as we go up. And then 6 would be right along there. Okay, an electron can occupy any one of these positions. The lowest energy position is closest to the nucleus. So for a neutral hydrogen atom, the electron would occupy that position. And that's known as the ground state. And these N's reference energy levels. The higher the N, the higher the energy. Okay, so this is another way of looking at it. Right? 2 and 1 are very far apart. And notice that to get these visible colors, none of the electrons jump from here down to 1. Not for visible light. If they jump down to 1, you're getting into the ultraviolet. Right? That's a lot more energy. But if we jump from, say, 6 to 2, 5 to 2, 4 to 2, 3 to 2, we get those 4 visible colors. Oh, by the way, they mentioned a unit of measure for the wavelength that you could put together, I'm sure, but nanometer, remember what nano means, 10 to the minus ninth. So this unit of measure is 10 to the minus ninth meters. And we use nanometers because it gives us with a manageable whole number. Rather than saying, let's say if we had, what was one of them, 411? 411 nanometers is easier to use than 4.11 times 10 to the minus 7 meters. So we just say 411 nanometers rather than this one. Just easier to handle. But when you do your calculations, if you use a wavelength in any of these calculations, you have to use the meters. So you got to convert this one to that one before you can do the calculation. All right, this is another model. This one actually isn't to scale. It doesn't even show the nucleus. All right. These, this is the mathematics that Bohr proposed for his model. And he said the energy levels in the atom can be calculated from this formula. And there's that minus 2.178 times 10 to the minus 18th is a constant that is used to convert the other units in the equation, the other variables, into joules. So Z is the same as it's always been. That's the atomic number. Right. So Z, for hydrogen, it'll be 1. And N is one of these values. Right. So if we divide that by N, and N equals 1, then we say 1 times minus 2.178 times 10 to the minus 18. That's how many joules is here. Now, if we go up to 2, then that gives us a half of that value. And that means the value is getting smaller. It's a smaller negative value. The larger negative value is close to the nucleus. It's the lower energy. And we come out here and they get, they're still negative, but they're getting smaller negatives as we move out until we reach infinity. And then they drop to 0. Because if you make N equals infinity, if you ionize it, if this is infinity, right? What's anything divided by infinity? 0, isn't it? Or it's the other way around. Infinity divided by any number. No, it's the other way. If you make infinity in the denominator, it's equal to 0. Yeah, I'm trying to remember my math from, I don't know what, 60 years ago. Okay. So, and only one electron can be present. So if we use a hydrogen-like atom, say lithium, then Z is going to be 3. And then that will change the position of these orbitals. Right? Because with more protons, we draw those electrons in. It draws things closer to the nucleus. So depending on how many protons you have in the nucleus, you will change the actual energy values calculated for that atom versus hydrogen. Okay. So if we know what the energy level is here and say, or we calculate it for here, and we calculate it for 6, then the energy given up if an electron goes from 6 to 2 is the difference between those two energy levels. So we take the final and subtract the initial. So what would the final be? Well, if it's going from 6 to 2, the final would be 2. So N would be 2 for that one, minus the 1 for 6 in the denominator squared. Okay? Now we can use a little math, simplify this equation, right? We can take out common factors like that constant, put it on the outside, and now what we have to do is subtract z squared over, actually, since they're all squared, the one on the left could be z over n final squared minus z over n initial squared. And if we simplified it for a hydrogen atom, actual hydrogen atom, then it would look like this. Okay, it's just math. And that energy difference is translated into the wavelength of light, or the frequency of light that's emitted. It should equal, if we make that energy calculation and put it here, and then divide it by this, we should get the frequency of light. It should agree with the experimentally determined value. So let's see, from 5 to 2, we get light 434 nanometers. If we take that formula and calculate the energy for that jump from 5 to 2, we get this much energy. And then if we take Planck's equation and calculate the amount of energy for that particular wavelength of light, we get almost the same value. 4.57 versus 4.577. So they're in agreement. Okay. The Bohr model correctly fits the quantized energy levels of the hydrogen atom and proposes only a certain allowed circular orbit for the electron. That's assuming the electron is a particle. And there's ample reason for believing that the electron is a particle because Millikan confirmed its mass. Right? So if it's got mass, it should be a particle. Right? Well, here's the problem. If it's a particle orbiting a central sun mass, then eventually the orbit should decay and the electron should spiral in, but they don't do that. So that was one of the problems with the Bohr model. It wasn't strictly planetary in nature. Also, as the electron becomes more tightly bound, it's drawn closer to the nucleus. Closer to the nucleus. And as a consequence, we're given a more negative value relative to zero energy. Zero energy is at infinity. So relative to the nucleus of that atom, the electron now has zero energy. It's been released from the system. Okay, in addition to that spiraling thing, the Bohr model is incorrect because it only works for hydrogen. It will not work for polyelectronic atoms. So if we tried to use it for helium, neutral lithium, or any of them, it would completely fall apart, wouldn't work. Because those electrons out there they still have their negative charge, and negative charges repel one another. So once you get more than one electron out there in that space, they start modifying the quantum nature of their environment. So the Bohr model only went so far. All right, so these jumps show us that the shorter the jump, the longer the wavelength, the lower the energy. Okay. Let's digress for a moment.
Oh.
We're going to introduce something called the Heisenberg uncertainty principle. Werner Heisenberg was another brilliant mathematician and physicist. And the problems they were running into were very complex in nature. And I put names of contributors down there at the bottom because there was interaction going back between and among physicists to try to figure out what's actually happening with the atoms. Heisenberg proposed, one thing that the planetary model would do was it would tell you exactly where that electron's located. And it would tell you how much energy it had, how fast it was going. Well, okay. It's only 4:30, right? We go till 5:30, is it? Okay. But if the Bohr model were not correct, then maybe we can't know exactly where the electron's located. We know something about its energy. Through lots of complex mathematics, Heisenberg came up with this formula. And this is actually a simplified version of the formula, just to illustrate oops, not two. I'm thinking of something else. 4 pi. So this is the Greek letter rho, and it means mass times velocity. It's the term that's used for momentum. Mass times velocity is momentum. So if we're talking about one particular particle, like an electron, then the mass is constant. And then we can put the mass out here, and we're only interested in change in velocity or change in energy. Okay. So what Heisenberg is saying is, these are two measurements that can be made for any object. Me, this marker, an atom, an electron, subatomic particles, they all fit this scenario. And what we're saying is that the difference between its position, if we need to narrow down, make this really small, if we can make this small, then we can know exactly where it is. But if we make this small, then this one has to be big, right? To keep it greater than that value. Okay. But if we're talking about subatomic particles, then this value right here is going to be very, very small. And this is probably going to be very large. Right? They're going to be moving fast. So if we're going to find out anything about the energy of the particle, which is where we're going with this, the energy, then in order to keep it bigger than that, to narrow this down, to make that small enough so that we know what the energy is. This is a difference. This is not an absolute value. This is a difference, a change in energy. If we can narrow that down so that we know the energy of the electron, then this has to be really big to keep it greater than that value. So what that says in English is that we can't know both where it is and how fast it's moving or how much energy it has at the same time. If we know one with precision, with accuracy, then the other one is sky's the limit. And that works. That's particularly troublesome for very small particles like electrons, like atoms. For stuff that's big, like me, right? This is really big, and I'm probably not moving very fast. So you can locate where I am with fair certainty because this is big enough, right, to take care of that. So this is going to be small difference and you can identify where I am. So that's characteristic of large masses. Large objects are not troubled so much by this relationship. It's only when you get really small that, so we have to decide, do we want to know where the electron is or how much energy it has? We have to make a choice. And most of the time, we're more interested in how much energy it has. And we settle on its position statistically. We say the electrons are probably going to be in this space. We don't know exactly where, but they'll be in here somewhere. So that's the way we approach electrons for the most part. Okay, this idea of the wave function, now we're getting into quantum mechanics. In order to describe things that are very small, we have to work with probabilities. And one of the variables that is introduced into formulas that govern quantum mechanics is the psi function. That's what that letter is. Got anybody who's sorority or fraternity? Know anybody? Some of them have these Greek letters in them. One of them, I don't remember which one it does, has the psi. That's a Greek letter psi. And in the function where it's used, it's a squared value. And that square function of psi indicates simply the probability of finding an electron near a particular point in space. Right? And the computers will draw out what we think the preferred place in three-dimensional space that the electron would be at a given energy. So these are all probabilities. When you see a diagram of electron orbitals around in a space, you're not looking at a true representation of the orbital. This is a probability. Where is that electron most likely to be located? Because we're not so much interested in that, although it does give us some information, but we're more interested in its energy. The wave function, as you get further away from the nucleus, as you go to the right on the x-axis, the probability of finding the electron in that space out there drops way, way down. So for this 1s orbital, which is the lowest energy position for the electron, it's going to be close to the nucleus. It's not going to be right at the nucleus. See, it drops down to 0 there, and then it rises to a peak and then tails off. So that gives us a better idea of actually where we're going to find the region of space where it's most likely to be located. Okay. Orbital size is difficult to define, and that's because of Heisenberg's principle. If we're more interested in energy, then we have to give some on position. So defining the position of the electron and the space that it might occupy, which is defined as an orbital, is difficult. So we use this wave function, which is derived statistically. And we draw what we call an electron density map. So the more dense the representation, the more likely you are to find the electron in that space. All right. Now we're going to get to describe the the quantum equations that were developed for this particular branch of chemistry and physics. Let's see, I'm trying to remember who proposed most of them. I don't think it was Heisenberg, it was Schrodinger. Erwin Schrodinger came up with these, and they've been refined over the years. But these equations have several variables where you can plug in values. So that's what we're getting at. We're getting at the values, and there are four of them, four numbers that go into these equations and define the probability, the wave function for the electron at any given energy. So the first one is the principal quantum number, and it's related to Bohr's model. The principal quantum number is n, and it can be 1, 2, 3, 4, on up. And this principal quantum number relates to both the energy and the size of the orbital. So the larger the value, the higher the energy, and the bigger the space. Okay. Okay. The second one is derived from this one. It's the angular momentum. I'm not sure why they call it that. Angular momentum quantum number. And this is designated by a letter L. Now, one thing about these quantum numbers is they're kind of nested or branching. So for this one, it'll produce a certain set of L's. This one will produce a different set, and this one produces a different set. So depending on where you start here, you get a different set of L's. And L takes the N and starts with 0 and goes up to N minus 1. So if you're starting at N equals 1, 0 is the only possibility. N minus 1, that's it. If you're starting with 2, then you can have 0 and 1. If your principal number is 3, you can have 0, 1, and 2 that are available for electrons. Now, I'm not saying they're occupied yet. That's just, they're available. The angular momentum. Now, what does this refer to? The angular momentum refers to the shape of the orbital. So the 0 will be spherical. The 1 will be dumbbell shaped. The 2 will kind of be dumbbell and some of the little donuts in there. So it gets more complicated as you get bigger, these numbers. And let's see. I was going to say something else. Oh. Let me make some room over here. Some textbooks refer to this one as a shell. This one as a subshell. And then the next one down is M sub L, or the magnetic, M for magnetic. The magnetic quantum number. And this is based upon L's. So in this case, you can go minus L up to 0 to plus L in whole number increments. All right, so if you have 2, you could go minus 2, minus 1, 0, plus 1, plus 2. At that level, then you can have that many M sub L's. And these refer to orientation. So you have a particular shape. Well, that shape is pointed that direction. Okay. The last one is the easiest one. The M sub S is the spin quantum number. And this can either be minus 1/2 or plus 1/2. Okay. And that's just a reference to angular momentum. So the electron can either spin this way or it can spin this way. All right. So those are the 4 quantum numbers that we need to know to draw out the electronic configuration of any element in the periodic table. So if you have a 1, you can only have a 0 here and a 0 here, but you could have 2 there. So if you're at n equals 1, actually S is the only one you can have. And it can only have one, let's see, this is orbital, excuse me. There we go. Shell, subshell, orbital. You can only have one orbital here. And I like to, if I need to use them, I just draw a line there to put electrons on it. And at this point, we're down to here. Now we can have 2 electrons there maximum, right? And I give them a plus 1/2 spin up, minus 1/2 spin down, if you have 2 of them. So this would be with 2 electrons and that's it. That would be helium. If we only had 1 there, it'd be hydrogen. So this would be helium with 2 electrons. The next highest energy would be, we've already used that one up, so the next one would be 2. 2, and for that one, you can have a 0 or a 1. Now, I didn't explain this. Let's see, let me put a 3 in here. Notice that we're using letters instead of numbers. Instead of saying 1, 0, which would be very confusing, right? We assign letters to these. Zeros are s orbitals or s subshells. 1 is a p, 2 is a d, and 3 is an f. And as it turns out, that's all we need to fill out the periodic table. Now, there are others available. You can go up higher. Like if you promote electrons into higher orbitals that aren't ground state, then you can put them in there. So the next one will be 2, and the next highest level on 2 is 0. So we have 2s, and it can have a maximum of 2 electrons in it. So what's next? Well, at 2, we could have a 0 or a 1. So that means at 2, we can also have a p orbital. Excuse me, p orbitals. Because when you get to 1 here, it can be a -1, 0, or a +1. So now for p, you can have 3, right? -1, 0, +1. And each one of these can have 2 electrons in it with opposite spins. So maximum, you could do this. So at n equals 2, you can have 2, 4, 6, 8. 8 maximum electrons in the n equals 2. And that's what they're trying to show you here, except they're not including electrons in it. But every time you jump up one more, you add another L, and that adds another possibility for M sub L's. Because if we went from 3, that means we'd also have access to 2, which is D. So we can still have 3S, we can have 3P, but now we can have 3Ds. This has 1, this has 3, and D being 2, it can have -2, -1, 0, +1, +2. It can have 5. 1, 2, 3, 4, 5. So if we put 2 electrons in each, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 is 18. We could have 18 electrons at the 3 level maximum. And then F, of course, would be, you'd have to go up to 4, n equals 4, excuse me, to get F's. And with 3, you can have -3, -2, -1, 0, +1, +2, +3, 7. You could have 7 orbitals in that subshell. But you'd have to be up to 4 to get there. Okay. Now for principal quantum number, let's see. Am I going to make it? I'm going to have to hurry. Principal quantum number n equals 3, determine the number of allowed subshells, different values of L. Different values of L. So if we've got n equals 3, then the allowed L's would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 9 subshells. Oh, wait a minute. Oh, different values of L. Okay, different values of L. My mistake. If it's 3, you can have 0, 1, or 2. I was going too far. That's subshells. I was going all the way to orbitals. So you can have 3 subshells. 3s, 3p, and 3d. For L equals 2, what are the magnetic quantum numbers? Determine the magnetic quantum numbers and the number of orbitals. So if L equals 2, then you can have -2 to +2 is 5. You'd have 5 magnetic quantum numbers. And there they are. Okay. Now, if the orbital is S, if it's 0, then its shape is going to be spherical. But it's not a solid sphere unless it's n equals 1. If n equals 2, then you have a region of space where the probability of finding an electron drops to 0. That's what that second graph shows. Notice it comes down and drops to 0 and then goes back up and then down. That's one position that's 0 before you trail off to the right. That's called a node, where you have no probability of finding an electron. If we go to 3s, it's still spherical, but now we have 2 nodes. For the p orbitals, right, L equals 1 is your p orbitals, and that's talking about shape. Now the shape looks like a dumbbell. And you can have 3 of them. Right? X, Y, and Z, or -1, 0, +1. And the scatter diagram on the left shows the probability, the electron density probability. So you're likely to find your electrons in this region here, maybe out here, but not so much. And like I said before, these have never been observed. Right? This is not direct observation. This is purely theoretical, computer generated, based upon the quantum equations. The Ds have 5 possibilities, right? And their shapes are double dumbbells, except for the last one. It's got a donut on it. And then F is really wild. I'm not going to hold you to those. I tend to focus on the P's because they make more sense. You got 3 of them, right? One dumbbell is on the x-axis, the other dumbbell's on the y-axis, and the third dumbbell's on the z-axis. That makes a whole lot more sense to me than the rest of these. And then there's electron spin. Now we've got certain rules that help us stay out of trouble when we start building atoms one at a time and adding more electrons, and they go into the next highest energy level. And these rules we start with the Pauli exclusion principle, which simply means that for any given atom, no two electrons in that atom can have the same set of 4 quantum numbers. Now, if they have the same N, L, and M sub L, that means they have to have different M sub S's. Or any combination, but they cannot, no two electrons can have exactly the same quantum numbers. That puts them in exactly the same space, and they're both negative. You can't put two negative charges in the same space. They won't allow it. So that's the Pauli exclusion principle. This is just another reason why we have to work with probabilities. When you start getting more than one electron in that outer space, it's these polyelectronic atoms, they interact. The electrons interact with one another, and they change the energy levels by that interaction. That interaction plus the buildup of nuclear charge affects where those the energy levels that can exist. So even though we can calculate them with these values, right, the equations are set up so that when you have more than one of these, they adjust for the relative energy positions. And this little diagram, it's kind of hard to see back there, but we normally think of this being the lowest energy, and then this is the next highest energy, but the P's are slightly higher than the S's. And the same here. These are slightly higher than that S. These are all higher than that. And then this one is just a little bit higher than that P. Okay. That's what we're trying to show there. And then they've got 4S there. And 4S, it's getting really close to 3D. All right, this penetration effect is kind of, sometimes it's difficult to understand. But what the penetration effect is trying to describe is why an s orbital has less energy than is more stable and lower energy than a p orbital. So if we draw them like this, so we've got a 2s and a 2p. Notice that the major hump on the p is closer to the nucleus in energy level than the s is, the major hump on the s. But the 2s has a node, and part of its electron density is closer to the nucleus than the p. So the 2s penetrates closer to the nucleus than the p does. That's what the penetration means. And you can apply this principle to others, right? So for this one, it's got 2 nodes in it. So this is likely to be a 3s, right? It has 2 penetrations, closer to the nucleus than, say, the 3p. So there we have the 3s, 3p, and 3d drawn together. The 3d has just a single broad hump. The 3p is a little higher in energy, but it penetrates closer than the 3d. But the 3s, even though its major hump is outside the d and the p, it penetrates even closer than the other 2. So this is, like I said before, this is all probability based. And it's like any theory or collection of theories. The theories are only valid as far as they can explain the natural phenomenon. And so far, the quantum mechanical equations have been very good at predicting behaviors. All right, let's get to the periodic table before I run out of time. A little historical note. Certain scientists were noticing similarities with the chemical and physical behaviors of certain elements. And Johann Dobereiner was one who proposed his triads. At that time, they didn't know, all 118 elements. They maybe knew half of them or even less. So Dobereiner noticed that certain elements had similar characteristics, like the halogens, chlorine, bromine, iodine. He may have also noticed that the alkali metals, lithium, sodium, potassium, had similar behaviors. He just called them triads. And that's as far as he took it. But scientists were starting to realize that there were similarities that their theories couldn't explain why they were similar. And they were still, at this time, they were still working on masses. That's all they knew. They just knew masses of different elements relative to one another. Some of them were the wrong masses, but they knew relative differences. Along comes Julius Meyer and Dmitri Mendeleev. Meyer was German, Mendeleev was Russian. And they both, about the same time, proposed arrangements of elements in a table form that would account for some of these similarities. Okay, so Meyer proposed his, but he didn't take it, he didn't develop it. He just said, this is what I think their relationships are. That's it. Mendeleev must have been obsessive compulsive, because he put things in his table and he noticed, since he only knew masses, he noticed that if the next element, known element, would go in order, and in his table would be in a family that didn't have the same characteristics. Like he would maybe come over here to zinc, and the next one that they knew was, say, germanium. Said, if I put it here, it doesn't look like boron, aluminum, and indium in its behavior. He says, so I'm going to leave this thing blank. Germanium is more like carbon and silicon, so I'm going to put it here. Okay. He did that in several places where there were unknown elements. He didn't stop there. He actually proposed and calculated some values, say masses, chemical behavior, physical properties, and assigned them to that empty space. He said, one of these days, somebody's going to find an element that fits that place, and it's going to have these characteristics. And sure enough, they did. So they filled in his table later with these elements, or he filled them in before he died. I'm not sure which. And that's why Mendeleev gets the lion's share of credit for the periodic table, because he used it to predict. Now, his first table, these families, these groups that were similar, in his first table, they were like this, left to right. His second publication switched them to what the arrangement's now. So we have the groups that have similar characteristics, and then we also have periods from left to right. So the reason for the period is based on the idea of periodic motion. Got physics, anybody? No. Periodic motion is the motion of an object that goes through a cycle, and it moves to here and it comes back where it started. Think of a pendulum. Periodic motion goes out here, comes back here, goes out here, always comes back to this position. On a periodic table, if we go, say, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, then the next one above that would be sodium. But if we put sodium out there in its own column, that would be a waste, because sodium is like lithium. So we swing back around and put it in that column. we've gone through a period and we're back where we started. Okay. So let's see. Did I give you extra credit for building the periodic table yet? Yeah, okay. Yeah, to help you learn the symbols. Okay, so you know some of these groups have names. Alkaline metals, alkaline earths, nitrogens, chalcogens, halogens, noble gases, the big group in the middle of the transition elements, and then the lanthanides and actinides. Okay, so they have, some of them have names. The first two and the last six columns are called the representative elements. I think because they are more well behaved when we look at trends, which we're going to do in a few minutes. When you get into the transition elements, they just kind of roller coaster. Those numbers at the top, I had you number yours at 1 through 18. That's the new numbering system. The old numbering system actually gives you information. One electron in the alkaline metals only has one electron in its s orbital. All of them. So that means if it loses that one, they're all +1 charge. That's why when you write the compounds, you balance lithium, sodium, potassium, rubidium with a 1+ charge. That's it. That's all they can afford. So 1A, 2A, jump over to boron, 3, 4, 5, 6, 7, 8. Tells you how many electrons are in that outermost shell. And that's where the chemistry happens. Okay. So we can divide the table into metals and nonmetals, and you already know about that. And that zigzag line that I had you draw in there, the black line, divides the metals and nonmetals. Right next to that line are some elements that sometimes they act like metals and sometimes they act like nonmetals. Those are the metalloids. Now this particular chart puts boron in the nonmetals, but some authors put boron in as a metalloid also. So metals on the left, nonmetals on the right, and then you have the transitions in the middle and the lanthanides and actinides. Now, we talked about the Pauli exclusion principle that says no two electrons can have exactly the same 4 quantum numbers. The next principle is the Aufbau principle. That's a German word, and I'm not sure what it means. The effect that it has on how you build an atom is when you add a proton to go to the next element and you add an electron to go with it, that electron goes in the next highest orbital, energy orbital. You don't put it way out here just because you feel like it. It has to go in the very next lowest energy level, right? That's the Aufbau principle. Now, that means that we have to know the sequence of orbitals from left lowest energy to right highest energy. Right? And I'm going to show you how to do that in a minute. But first we need to, well, I'll tell you what, let's do that first. So if we put them in order of energy, they would go like this. Five S or D 5P. That's far enough for now. Increasing energy from left to right. Notice that we get some switchbacks in here. 4, then we drop back to 3D, then to 4P. So 4P is higher energy than 3D. And I'm going to show you how to do that from the table. Actually, there are 2 ways you can do it. So if we build oxygen, which has 8 electrons, oxygen would be 2, 4, 8. because we can have a maximum 2 here, maximum 2 here, and a maximum 1, 2, 3, 4 there. Maximum 6 here, but we only need 4 for oxygen. That leads us to Hund's rule. Hund's rule says if you have a set of orbitals in a subshell, right, so P would have 3, D would have 5, I don't have any F's up there, but they would have 7. When you put electrons in there, they must occupy separate orbitals until these orbitals are filled. And if you have any extra electrons, then you can go pair them up. But the lowest energy state would be separate electrons in these orbitals. If you pair them up in the same orbital, then you have the repulsion problem. So Hund says these orbitals are known in chemical terms as degenerate. They're not morally aberrant, right? The degenerate means they're the same energy level. That's Hund's rule. And there's oxygen examples. So where we put like that. That would be ground state, neutral oxygen. Now the concept of valence electrons, those are the electrons that have the same principal quantum number. So in this case, the valence electrons for oxygen would be 2, 4, 6. 6 valence electrons. Notice that the Roman numeral over oxygen is 6A. That's where they got it. 6 valence electrons. Now we can divide the periodic table into regions where different orbitals are being filled. Right? The first and second columns are s orbitals. Right? The alkali metals only have 1 electron in the s. Well, that's not an example. Say we had sodium. Right? That's 11. So that would be here, 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 and there. This one, this one, and then 3s there. So this will be 2, 4, 5, 6, 7, 8, 9, 10, 11. So that 3s orbital has like that. And everybody in that family has a 1s. So the first 2 columns, the alkali metals are S1s, the alkaline earths are S2s. Then when you get to the right-hand side for the P's, notice that for the S's, you can only have 2 for the S's, 2 maximum. That's 2 columns. For the right-hand side, how many can you have for the P's? 2, 4, 6. You have 6. So if you notice boron, carbon, nitrogen, oxygen, fluorine, neon, 6 elements. We're filling p orbitals on the right-hand side. Well, except for hydrogen and helium, they're separate. Then if you have to go to d orbitals, they're in the middle, transition elements. So scandium is in the 4th period. Potassium, calcium would be 4s right here. But once you get those filled, you go to the Ds. So you go from calcium to scandium, you drop from a 4s to a 3d, and then you fill the Ds. 3d, 1, 2, 3, 4, 5, all the way across to zinc. Now you've got 10 out of those 5 orbitals. And then you go back to 4p's with gallium. Okay? And you keep doing that. So if you once you get to the D's, you just drop down 1, say 4 down to 3, 5 down to 4, and fill the d orbitals. Now, when you get down to lanthanum and actinium, you have to digress from lanthanum, then you go down to the lanthanides, and you fill f orbitals. And remember, f is 3, so it's -3, -2, -1, 0, so 7 orbitals, or 14 electrons, 14 protons, 14 elements. So there are 14 elements across that bottom, filling f orbitals. Then when you get finished with lutetium, you come back up to hafnium, and you're off again with, let's see, 3D, 4P, 5S. Oh, I didn't get down to 6. Okay. You're down to 4 Fs with the lanthanides. So they drop down 2 principal quantum numbers to get to the Fs. So cerium starts with lanthanum to cerium goes to 4F rather than from 6 to 5D for the transitions, but the internal transitions, the lanthanides, you drop down to 4F. So you drop down 2. Okay, and now we can build any atom we want to. Let's see if we got an example. This is the way you would do it if you don't have the periodic table. You just set up 1s, 2s, 2p available, 3s, 3p, 3d, 4s, 5s, 6, and 7s. Set those up, and then you draw your diagonals. Diagonal for the 1, 2, 2p, 3s, 3p, 4s, and then you go to 3d. And that's what you see here and what you see there. All right. I just got a few minutes. I'm running out of time. Electronic configuration for sulfur. Right. So let's get rid of these. And sulfur. How many does it have? 16. Okay. Fill this one up, fill that one up, fill this one up, fill that one up. And let's see, that's 10, 12. 12 and 6. Oops, too many. 4, right? So that's 10 and 6, 16. So this would be sulfur. And if we went to the periodic table and did the same thing, we would say we need 16. So we go hydrogen to helium with 1s2. Then we come down to lithium, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, sulfur. And we got our configuration. Barium is a big one. So rather than go, now if you're told to do the complete electronic configuration, you have to do the whole thing. But if you're not, then you can use a shortcut. Barium is 56. But notice that barium is just beyond xenon. See, xenon is 54. So it's going to have the same core as xenon. And then what's beyond that is period 6s. 2. That's barium in abbreviated form. I'm not going to do europium. That's down in the lanthanides, and it's just too much trouble and not enough time. But I will. Oh, and if we do, we can do sulfur the same way. If we start with neon, then we can fill in the rest. And what that does is that puts the core here, and these, everything over here is valence. Okay, periodic trends. I'm running out of time. We go to 5:35. I got 15 minutes. Let's see how fast I can get these trends out of the way. In the periodic table, we notice trends for various physical characteristics. Ionization energy is the first one we're going to look at. Electron affinity is the second, and atomic radius. So what is ionization energy? Ionization energy takes an atom in its gas state, and we add energy to it in some form, and we kick off one electron like that. It's still gas, but now it's a +1 charge. Okay, this is the ionization energy. This is the first ionization energy because it gets rid of the first electron. You can have a second ionization energy if you take this one and add energy to it, and that leaves that plus another electron, and it'll have a different energy, usually greater amount of energy required, because you're trying to remove a negative from an already positive charge, and it takes more energy. Plus, you're trying to remove an electron probably from a lower energy state. Okay. Why is this a gas? Because if the standard state of the element is, say, a solid or a liquid, then before you can get rid of the electron, you got to add enough energy to get those atoms apart from one another, from the solid state and the liquid state. So this energy is expressed in terms of the monatomic gaseous atom for that element, regardless of how it's most stable at room temperature. That way, we remove any additional energy required to get it to that state. And now we're just looking at how much energy it takes to remove the electron. And here's magnesium. First ionization energy is 735 kilojoules. Second is 1445. So we're doubling it for the second one. Where are those electrons coming from? Magnesium, they're coming from the 3s orbital. The first one, 3s2. Now we're down to 3s1. We take that 3s1 away. Those first two electrons are valence. They're outermost electrons. Those are the reactive ones. If we go to the third electron, where is it coming from? It's like trying to take an electron from neon, right? We're trying to remove core electrons now. And when you try to remove a core electron, the energy cost goes way up. In this case, the first core electron is 10 times as much energy as the first one. All right, so what's the trend in the periodic table? All right, if we draw us kind of a representation of the periodic table, over here like this, down here like this, like that, like that. The ionization energies increase from left to right. So if we go across here like this, first ionization energy increases. And that's primarily due to the increase in nuclear charge. We're adding more protons to the nucleus. Even though we're adding more electrons, more protons means a stronger attraction to the electrons. And since the electrons are going into essentially the same energy level, then we're not seeing any shielding. Okay, how about up and down? Well, if we go down, the ionization energy is decreasing. Because even though we're adding more protons, we're also adding electrons at lower energy levels that are shielding that positive charge from the outermost electrons. So as we go down, we're decreasing the ionization energy. And of course, going up is the opposite. So that means from lower left to upper right, first ionization energy increases. Let's see. Now we do get some anomalies. All right, we get, if we go lithium, beryllium, and then we go from beryllium to boron, we see that boron drops. If you look at that first line, go lithium to beryllium, and then boron drops because we're going from an s orbital to a p orbital, which is a little bit higher in energy, which means it takes less to get it out. So the energy cost for a p electron is decreased. But then it starts back up until you get to nitrogen. And then for oxygen, it drops back down again. Well, if we look at nitrogen versus oxygen, which is 8 and 7, then we get over to the p orbitals, the two p's. This p is only 3 electrons. This p is 4 electrons. Right? Those are separate electrons. But for oxygen, you got these paired. There's some repulsion effect right here. So that electron is easier to remove since it's being repelled by a little bit of energy to begin with. So that's the reason that we drop back down for oxygen before we go back up. Those are the types of anomalies that you see in these trends for ionization energy. Let's see. All right, we talked about that already. Which atom requires more energy to remove an electron? Well, the ionization energy increases from left to right, so sodium should be less, chlorine should be more. Now, we're in lithium-cesium territory. Cesium is further down, it takes less energy because its outermost electrons are further from the nucleus and shielded by core electrons. So lithium would take more energy. How about the second ionization energy for lithium versus beryllium? The first ionization energy would be a little bit higher for beryllium. But for the second one, lithium has already lost its only electron in that outer shell. Now we're trying to remove a core electron, which looks like helium. So the lithium's second electron will take more energy than beryllium's second electron because beryllium is still removing an s electron. So lithium should take more energy to remove the second electron than beryllium does. And here's a graph that came out of my textbook. And it shows you that the difference between that stair-step line shows you where the core electrons are for each of those elements. And you see for each of the cores, you get a huge jump in required energy. Electron affinity. Okay. See, that was ionization energy. Let's see, let's erase these so we can use this table again. Okay. Electron affinity actually takes that electron and puts it on the other side. So let's get over here. It takes the neutral gaseous atom and we're going to add an electron to it. And what does that do for energy? It releases energy. Right? When that electron goes from infinity down to the highest level orbital, we get some energy released. And remember when we were talking about thermochemistry, everything is relative to the system. So if energy is released, the value is going to be negative. Whereas energy added is valued positive. Okay, so these values are going to be negative. And the greater the negative, the stronger the affinity of this one for that electron. So the larger negative value means a stronger attraction for the electrons. Okay? Oh, I forgot my charge. There we go. So in general, as we go from left to right, this is electron affinity. The electron affinity becomes more negative because the attraction is stronger for the electrons as we add more protons. Okay? And similarly, as we go up, the electron affinity increases, becomes more negative, because now the electrons are being attracted to by a stronger nuclear charge that's not shielded, right? We're decreasing the levels, and we're making the electron that's being added, it's closer to the nucleus, and it can see more of the charge in the nucleus, and actually at a lower orbital level. So it gives off more energy when it comes from affinity to that lower level. So the trend here is electron affinity more negative. We can't say increases because that would imply positive movement. It becomes more negative, which implies a stronger attraction. Atomic radius. Okay. Atomic radius is a little kind of, it's personality dependent to some extent. It depends on how you measure the radius. The atomic radius is a little different for each type of element. Metals have a different way of determining atomic radius than nonmetals. Nonmetals, if you can form a diatomic with a nonmetal, then all you need is to determine, all right, what's the size of that group, then cut it in half, and that's your radius. But with metals, we have to look at them, right? So here's our example. If we know the distance between the nuclei, we just cut it in half, and that gives us the atomic radius. See, the atomic radius is a little difficult to get a handle on because we don't know where the electrons are. We know generally, right? But suppose when you get these two atoms close together, instead of just touching like balls, billiard balls, they actually overlap a little bit. So the numbers vary depending on who's quoting them. Okay. Metallic radius is fairly easy to determine with X-ray diffraction. Right? We fire electrons. We're going to learn about that next semester if you're still around, if I'm still around, with the Bragg equation. Will tell us, using X-ray diffraction, how far apart the layers in the metal are, and that gives us an indication of the radius of the metal atoms. Covalent radius, we use different types of approach. Sometimes we can use X-rays, sometimes electron microscopes, neutron diffraction, microwave spectroscopy, various other reasons. And the best researchers will use multiple methods of determining the radius and then look at the results and say, all right, how are we going to blend these together and get a representative value? See if they agree with one another. All right, as far as the trend in the periodic table, the atomic radius tends to decrease from left to right. Well, let's just do it this way. From left to right, R decreases. And that's simply because you get more protons, a higher nuclear charge that's drawing on those electrons and pulling them closer to the atom as you go from left to right. If you go down, then you're adding principal quantum numbers. You're adding layers, right? So that puts them way out here. And this is R decreases. Yeah, decreases this way. Okay. So the trend for, wait a minute, decreases. No, increases. I'm sorry. I know that didn't sound right. R increases because we're adding layers. Increases. So it decreases the other way. It decreases from left, lower left to upper right. So the smaller atoms will be up here, the larger ones will be down here in general. And there's a representation. Notice that we're only using the alkaline metal, alkaline earth, and the representative elements. Right? We skipped over the transitions because they do that roller coaster thing. Okay, which is larger? Well, sodium should be larger because it's on the left-hand side. Lithium and cesium. Cesium is much further down. It should be bigger. Let's see. I'm out of time, aren't I? Okay. Final thoughts? Okay. So when we talk about individual orbitals, which one is larger? Well, hydrogen 1s versus the lithium 1s. The lithium 1s should be smaller because it's being drawn in by 3 protons, and hydrogen's only got 1 proton. So the larger one should be the 1s from hydrogen. When we're just talking about individual orbitals, which is lower in energy, the one that's closer to the nucleus. Now we're talking about lithium. Okay. I'm going to have to just give you these and you see if they make sense to you. Okay, final thoughts. I'll just leave that long enough to get it recorded and we'll move on. There we go.